earlier video, I had seen bilinear from inner product and positive definites. In my earlier video, I had seen symmetric positive definite bilinear from always inner product. And for review, just see what is the bilinear form, because today's goal of this lecture is I will say different type of example which had come in different type of comparative exam based on bilinear property. So at first, just a review, see the bilinear form. What is bilinear form? We all of us know if V be a vector space over the field R, then we can tell a bilinear form on the vector space V is a function which is mapped from V cross V to R such that it is linear in each component. That means f of lambda u plus mu v comma w equal to, we can write this as lambda times f of u comma w plus mu times f of v comma w. Means this is bilinear in the first component. Also it is bilinear in with respect to second component. Then we can tell with respect to second component f of u comma lambda v plus mu w equal to lambda times f of u comma v plus mu times f of u comma w. Okay, and this is the idea of the bilinear form. That means this is linear in both component with respect to both component, and a bilinear form is always symmetric if f of u comma v equal to f of v comma u, and this is true for all uv belongs to the vector space. And a bilinear form is positive if f of v comma v greater than 0, and this is true for all v belongs to the vector space V. And a bilinear form is positive definite if f of v comma v strictly greater than 0, and this is true for all non-zero vector v. Then this is called as positive definite. And symmetric positive definite bilinear form is always inner product. We all of us know this. And a bilinear form is negative definite if f of v comma v is strictly less than 0 for all non-zero vector space v. Indefinite if there exists non-zero vector v comma w such that f of v comma v strictly greater than 0 and f of w comma w strictly less than 0. Then we can tell this bilinear form is a indefinite bilinear form. Have you understood? And in my previous video, I have discussed couple of example which all symmetric but not inner product. That means this is not positive definite. For example, if we consider the vector space equal to R2 such that f of x1 comma x2 y1 comma y2 equal to 2x1 y1 minus x2 y2. Now the question is f is bilinear form? Second, f is symmetric, f is positive, and f is positive definite. Obviously, this is bilinear form because it is linear in first coordinate, also this is linear in second coordinate. So obviously this is bilinear form, also this is symmetric, but this is not positive definite, because positive definite means f of v comma v, so x1 comma x2 comma x1 comma x2, this would be 2x1 square minus x2 square. But this is not necessarily always strictly greater than 0, because as positive definite means f of v comma v, here v, since v equal to R2, therefore this would be x1 comma x2, x1 comma x2, then this value would be 2x1 square minus x2 square. And this is not necessary, this is always strictly greater than 0, because if you choose the particular vector x1 equal to 0 and x2 equal to 1, then this value would be minus 1. which is strictly less than 0. Or we have got one non-zero vector. For this mapping is not positive definite. Have you understood this concept? That means this is symmetric bilinear form but not positive definite. So this is not example of inner product. That means from this idea I have got to verify a space is inner product or not. If we can to find the space is bilinear and symmetric positive definite, then always this would be inner product. Have you understood? Okay. But if we consider this mapping in R2 f of x1 comma x2 y1 comma y2 equal to, here given 2x1 y1 minus x2 y2, but if we consider 2x1 y1 plus x2 y2, then this is always would be strictly greater than 0. F of x1 comma x2 always would be strictly greater than 0. Okay. Therefore this is always inner product, but this is not be inner product. Have you understood the process to verify inner product? Okay. I will say another example. Consider a bilinear from f of R2 cross R2 to R such that f of x1 comma y1 x2 y2 equal to x1 y2 minus x2 y1, and this is obviously bilinear from because it is linear also first component and second component also. So this is bilinear from, but this bilinear from not symmetric because here f of x1 y2 x1 y1 would be minus of f of x1 y1 x2 y2. Have you understood this process? Okay. Also this is not positive definite because f of x1 comma x2 and x1 comma x2, this would be obviously x1 x2 minus x2 x1. That means this value is always 0. So for all non-zero vector this value is 0. So this is not positive definite. So this is not symmetric, not positive definite, but this is bilinear from. So this is not also inner product. Okay. In my previous video I had seen, given V and W be vector space over the field A and consider the set B which contain the vector V1, V2, Vm, and consider the set C which contain the vector W1, W2, Wn, then consider a bilinear mapping F from V cross W to F. This is a bilinear from, then there exists a unique A which will be the M cross N matrix over the field F such that f of V comma W equal to V transpose AW, and here this V transpose means small v transpose. This is the coordinate vector with respect to the basis vector, and small w means this is the coordinate vector with respect to the basis vector C. And here this A would be such type, if we consider 3 cross 3 matrix, then this would be inner product U1 comma U1. These entries would be inner product U1 comma U2, inner product U1 comma U3, inner product E2 comma U1, inner product U2 comma U2, inner product U2 comma U3, inner product U3 comma U1, inner product U3 comma U2, and inner product U3 comma U3. And obviously this matrix always would be symmetric from, and when f of VW equal to f of WV, then obviously U1 comma U2 and U2 comma U1, this inner product always would be same. Similarly, inner product U1 comma U3, U3 comma U2, U1, this would be same. inner product u2 u3 and inner product u3 u2, this would be same. This is quadratic form when f of v equal to v transpose aw. That means from bilinear form we can generate one matrix, and also from quadratic form we can generate, sorry, here not w, here v, we can generate one matrix. Actual definition of quadratic form is a symmetric matrix A, and the quadratic form always denoted as qv equal to v transpose av. This is the quadratic form, and quadratic form is positive definite when for all non-zero vector v in Rn, v transpose av strictly greater than 0, then this is positive definite. And positive semi-definite if v transpose av greater than equal to 0. That means here equal to 0 when v equal to 0, then we can tell this is positive definite. And negative definite if for all non-zero vector v in Rn, v transpose av strictly less than 0. And negative semi-definite if v transpose av less than equal to 0, that means this is equal to 0 when v equal to 0. And indefinite if neither positive nor negative semi-definite, then we can tell form is indefinite. Let's see one example which had come in CSR net. The question is, which had come CSR net 2026 November 2020 exam. The question is, which of the following real quadratic form on R2 is positive definite? If we consider first question, here q of xy equal to xy, and if we consider x equal to 1 and 0, y equal to minus 1, then this value would be minus 1, which is obviously strictly less than 0. And second example, q of x comma y equal to x square minus xy plus y square. Okay, and this is always strictly greater than 0 for all non-zero vector x and y belongs to R2. Check it oneself. And notice in third option 3, q of xy equal to x square plus 2xy plus y square. If we consider q of x comma minus x, then this would be x square minus 2x square plus y square, sorry, x square, and this value obviously would be 0. Therefore I have got for non-zero vector in R2 q of xy equal to 0, so this is not positive definite. Similarly for in option 4, q of xy equal to x square plus xy, if we put q of x comma minus x, then this value would be x square minus x square, so also this value would be 0. So option 4 also not right option, only option 2 is the right option. Have you understood this concept? I hope my all viewers have understood. Also, to verify is a quadratic form is positive definite or negative definite or indefinite, there exists another method, and the method is such type. By quadratic form we can generate one matrix. There exist various rules to define a matrix is positive definite or not. Okay, but these rules I will see in my next video. Then I will define this question again by these rules by creating the matrix A. Okay, I will see another example of bilinear form in inner product. The question is, which had come session at December 2019 exam. The question is C01, which is actually the space of continuous real valued function on the closed interval 0, 1. Okay, and define one inner product f with g equal to integration 0 to 1 ft gt square dt. Then which of the following statement are true? Option 1, this is an inner product on C01. Option 2, this is an bilinear form on C01 but not inner product. Option 3, this is not bilinear form on C01. And option 4, inner product f with f get strictly greater than equal to 0 for all f belongs to C01. That means here we have to prove positive semi-definite property. At first I will check is this bilinear form. For this f of alpha g, because we have to check this is linear with respect to both f and g, and here inner product f comma alpha g would be 0 1 ft alpha gt whole square dt, and this is actually equal to alpha square integration 0 to 1 ft g square t dt. Okay, and this is actually alpha square inner product f comma g. So inner product f comma alpha g is equal to alpha square f comma g. That means here linear property has broken here, because for linear property we all of us know f of alpha g would be alpha times f inner product fg, and since here linear property has broken, that means this is not bilinear form. Okay, and since this is not bilinear form, so this is inner product, this is not true, because for inner product at first this is an bilinear form. Next I will say, is this positive definite, positive semi-definite? For this consider f equal to -1. Then inner product f with f, here the inner product is denoted as open integration 0 to 1 -1 dt. Here -1 and -1 whole square would be +1, and this value would be actually -1. So this is not strictly greater than equal to 0 for all f belongs to C01. So here only third option is true option. This is not bilinear form on C01. I hope my all viewers have understood this question in better way. Okay. Our next example, which had come session at December 2018 exam. The question is, consider one mapping. Here the mapping is denoted as B, which is defined from R cross R to R, which be a function such that B of A comma B equal to AB. Then which of the following statement is true? Option 1, B is a linear transformation. Option 2 is a positive definite bilinear form. Option 3, B is symmetric but not positive definite. Option 4, B is neither linear nor bilinear. Here easy to check linear, because here B of AB equal to A dotted with B. Obviously we all of us know this type of transformation not linear, because here second order. So this first option is always wrong option. And then I will check, is this mapping is bilinear? This is true, because B of C1 alpha plus alpha 1 plus alpha 2 comma B equal to, by definition this is C1 alpha plus alpha 2 comma times B, which is equal to actually C1 alpha B plus alpha 2 B. Okay, and this is equal to actually definition, this is equal to B of alpha 1, here alpha 1 comma B plus B of alpha 2 comma B. Okay, similarly this is linear by first component, similarly this is linear with second component. So B of A comma C1 beta 1 plus beta 2 would be, by definition this would be A times C1 beta 1 plus beta 2, and this is actually equal to C1 times A times beta 1 plus A times beta 2. Okay, and this is actually C times B of A comma B1 beta 1 plus beta B of A comma beta 2. So this is also linear with respect to second component. So obviously this transformation is bilinear from. Now I will check, is this transformation is symmetric? Obviously B of AB equal to, since AB, and B of BA would be also BA. So B of AB and B of BA always same, so symmetric. And next we have to check the positive definites. For positive definites, B of A comma A equal to A square, and A square, since the mapping is defined from R cross R to R, A square in real number always strictly greater than 0. So this is obviously positive definite. That means option 2 is a right option. B is positive definite bilinear from. Option 3 is indicate B is symmetric but not positive definite. This is wrong. Option 4, B is neither linear nor bilinear. This is also wrong option. Have you understood? Okay. Today I will stop here. In my next video, I will discuss different type of question of bilinear from, and I will discuss different method to define a quadratic from when be positive definite, negative definite and indefinite. And this topic is very important for higher study. Okay, soon stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.